Hello, everyone. This is the last in a series of lectures covering Chapter 18. Today, we'll be talking about beats, and to think about them, think about what a beating is. First, let's think about what we've seen so far in the chapter, which was superposition. Waves that are a bit out of phase with each other or moving in opposite directions, and then they combine on the same medium and they create a wave that has different amplitude depending on their phase. Now, then there's the standing waves where the waves are moving opposite to each other with the same speed and frequency. So you ended up getting the standing wave where the elements of the medium just moved up and down, but there was no visible motion propagation of the wave. So what could also happen, though, is that you could have two waves where they still say have the same amplitude, they're traveling the same direction, they just have different frequencies. And when they overlap, then you can see that having different frequencies means that the overlapping causes destructive and constructive interference at different points in space as the two waves travel. So the sound that makes, if it's sound waves, two sound waves with different frequencies are heard at the same time, then you'll actually hear then their superposition, their combination, and you'll get this sound where at points, it sounds like louder when the waves are actually aligning together, and then it'll sound quieter for a bit as the waves go into out of phase. Since even though their speed is the same, due to the different frequencies and wavelengths, they overlap differently over time. So, for example, if you strike a tuning fork which plays a unique frequency next to another one with a slightly different frequency, you'll hear the combination of their sounds, and it'll be something that has this periodically varying intensity. And depending on the frequencies of the two tuning forks, the periodic sound that you hear will be faster or shorter, or even too fast that you can't even hear the beating. By beating, we mean that in the sound there's some periodic variation in the amplitude at any given point. So that given point could be your ears, and that's because, again, you have two waves of slightly different frequencies superimposing, creating this variation in amplitude, which, again, for ears, that's just a variation in sound. So you show here on graph A, there's two waves, a blue one and a green one. And at this particular point in time, what you have is the waves overlap at some point and they don't in others. So over time, then, as a wave travels to the right, you have this areas, these envelopes, where the amplitude goes from constructing interference here to destructive, and then starts a new envelope where the two waves are now starting off with constructive interference, but then they start moving out of phase with each other until they reach constructive interference again. Now they're in phase, and they start falling out of phase, and once again reach destructive interference at the end of the envelope. So this is the resulting wave that they create, and the wave here is a normal wave, just that its amplitude obviously varies over the course of one envelope. And you can imagine then that if you were to graph this, say, as time passes, then you'd see all these packets traveling to the right, like these waves are. And everything else over the waves is the same, so they have the same amplitude and speed, and they're moving to the right. So when you combine the formulas for the two constituent waves, and their wave functions, look super similar. It's just that one has a different frequency than the other. We have frequency 1 and frequency 2. When you combine the wave functions together, you get the wave function here that describes the resultant wave function. And this tells you a lot about the beats and the resultant wave function inside each envelope. There's basically two terms in the wave function. The first term here in the square brackets is the envelope term. So this term is sort of responsible for modulating the amplitude of a beat as the beat occurs. So correct, because you'll know that a beat starts off with no amplitude and then reaches max amplitude and then goes back to 0 at the end. The second term here is a resultant wave term. So this term kind of accounts for what the wave looks like inside the envelope. So this term here, this average with two frequencies, is actually the frequency of the waves inside the envelope. So the rate at which this crests pass some point in time is equal to the average of the two constituent frequencies. Then we call that the effective frequency of the resultant wave, since that is actually the frequency that the resultant wave has. But this term here, we call it the beat frequency because it modulates the amplitude that you get over a single beat. So over a single beat, the amplitude can go right from like 0 to the maximum 2A and then back to 0. It also determines the rate at which beats occur. So this term here, f1 minus f2 divided by 2, is a beat frequency. And the term here, then the 2A, this is like the actual, max wave amplitude, which again is modulated by this cosine term that depends on the beat frequency. So the beat frequency is the number of amplitude maxima that one hears per second. So imagine that your ear is receiving the sound here. This is one beat. So the beats are the parts of the wave that are tied off by these like tiny little peaks. So this to that is one beat, and then here's another beat. Then this is the end of that beat, and then you got another, and so on. So imagine that your ear, you're listening right here. If you count then how many beats come to you, then you hear a loud sound now. Okay, that's one beat, that's over. You hear a loud sound now, that's the second beat, and then the third beat will come, and you could actually count, okay, how many beats am I hearing in a second? Now in this case, this is a really slow beating, because you hear the one beat here, and then by the time you hear the next beat that's coming up now, more than a few seconds have passed. So the beat frequency is probably going to be like one beat every 5 seconds. You can actually count, or you can say, okay, here's my one beat, 2, 3, 4, 5, 6, 7, 8. So around every 8 seconds you hear a new beat, which means that your beat frequency is pretty big. Which I mean is really small, right? Because if you hear a beat every 8 seconds, that means that your beat frequency is one beat per 8 seconds. And you can actually deduce what the beat frequency will be by just looking at the frequencies of the constituent waves. So if you take the difference between the frequency of the two sources, that'll tell you how many beats occur per second, which means that the bigger the difference between the two sources, the more beats per second will occur. And for the human ear, we can only really hear like 20 beats per second. Anything higher than that, we can't distinguish the beats. They'll just sound like one flat sound. So that's why for tuning instruments, you can check if your guitar string's slightly out of tune by playing another string on the guitar, and you play them together, and you notice some beating, and that tells you that, yeah, okay, you're just a few. Your string is just a little bit out of tune. Its frequency of sound just a little bit off from what it should be, and that's why you hear some beating sound when you play both strings. Now, if you were super out of tune, then your string frequency will be way off from what it should be, and playing both strings at the same time won't help you because the beat frequency would just be too many beats per second. You won't be able to like hear that. So you kind of, as you tune your string to what it should be, and you play the other string to sound what it should sound like, you should hopefully be adjusting it so that the frequencies come closer together. And that will mean that the frequency of beats that you hear should decrease as you tune it. And eventually, once your string is perfectly in tune, you play both strings at the same time, then you will not hear any beats because there's no difference in their frequency. So there's an example here where there's two piano strings. They are about the same length. They have the same tune. And that means that, right, they're going to play a note, probably a C note. But then they're doing some adjustments, and now the one string increases its tension by 10%. So that's enough, right, to increase the speed of the vibrations in the string, which would make it so that the frequency of those waves would be a bit higher. So now the frequencies then between the two strings will be different, which means that if you play them together, you'd hear some beating. If you look at the relationship though, and again, this is two strings, so they're looking at the frequencies of a string that's fixed on both ends, and the relationship it has with the speed of a wave in the medium. The medium being a string, then you can relate that back to the square root of the tension divided by the linear mass density. And anyways, what you end up getting is that the frequency on a string is proportional to the square root of its tension. So if the tension on one string goes up by about 10% here, well, in this case, it will be 1% actually, then the frequency only goes up by a square root of that. So actually, the frequency only goes up by a half of a percent. So if that's true, then the frequency has only increased by 2 hertz. And then if you play both notes, you'll hear that one's a little off key. You'll hear like 2 beats per second when you play them. And that means that the strings are out of tune. They're both not playing quite a C note anymore. There's a nice video here from Flipping Physics that he talks about the whole adjustment thing and how you get a different sound if like your strings are out of tune, but when you tune them, you don't hear any beating. And there's I don't know if you can hear it actually. It just went on autoplay. But yeah, highly recommend watching it. It's only 4 minutes. And here there is a presentation. It's a activity where you can create 2 waves of any frequency and hear what their beating would sound like. And that's all for this chapter. The remaining sections are supplemental, so if you want to look them up, you're welcome to. There's some slides at the bottom that have the in-chapter examples worked out for reference, so you can keep scrolling if you want to find them. Anyways, that's all for now, so have a good day.